Welcome to today's webinar, which was titled Energy Audits Towards Higher Performing Buildings, which will be presented by Elvin and Ruya. Today's session will be recorded and will be available through IBPSA-USA YouTube channel. So if you have any issues hearing the presentation, please try calling in upon instead of using the computer audio. And this is a Zoom webinar, so you will be muted and off camera during the session, but feel free to participate by posting questions in the Q&A session at the bottom of your screen by entering any comments into the chat. By default, the chat is set to send to just presenters. So be sure to click down arrow next to the chat and select all panelists and attendees if you like to see your message. And we welcome your questions, thoughts, ideas too, as we continue to work towards IBPSA-USA's mission of fostering better buildings through simulation. So let me introduce you to Elvin Ruya. Elvin is a Texas-based professional engineer in mechanical engineering with more than 10 years of experience in both new construction and existing buildings, focused on energy efficiency, high-performance building design, and operation. She brings an extensive knowledge of high-performance building measures such as envelope lighting, HVAC, and controls to help building owners and designers to optimize their design. Elvin has worked with a variety of projects and clients, including commercial offices, hospitals, K-12 schools, universities, multi-families, airports, and stadiums, even more than I can count on. And her project experience includes energy auditing, advanced energy modeling, commissioning, retro-commissioning, measurement and verification, and construction management. Please join me in giving a warm welcome to Elvin. Stage is yours, Elvin.
All right, let me start my screen share real quick. Please let me know if you can see it well. Okay. Hi, everyone. Thanks for joining today. I'm Elvin. I'm a senior energy engineer at Noresco. I'm part of the sustainability team. And I'm based in Austin, Texas, as Aisha mentioned. So today we will be talking about existing buildings and how we can help to improve their performances through energy audits. Since we all know the codes are getting more stringent towards carbon neutrality, but is typically more aligned for the new construction projects. And but for us, the existing buildings are the elephant in the room, and they contribute so much energy usage and also carbon emissions. So that's why we are going to be focused on them today. So I mentioned most regulations are typically around new construction, but there are some, this is from the Department of Energy's website. There's this map that actually shows the building performance standards, because some states or cities actually have adopted them for the existing buildings. So each is, as you can see, kind of different. I believe Washington has started this, and they already passed the energy, and in some cities have like passed emissions, and some of them are under construction. California is like state level under construction for passing this law, or like New York has Local 97, which we know have very stringent penalties actually for the let me move this one around. So very stringent penalties, like failure to report, file a report is like 50 cents per square footage per month, or providing full statements are $500,000. So even though this building performance standard is not really clear about how to get they have different metrics. Some are like targeted to EUI, and some of them are targeted to the emissions. So we know there are the targets, but how to get to the target is actually the question. So that's how the energy audits come into play. So as you can see, in Texas, we don't currently have any regulation for the existing buildings. Maybe Austin will be the first, since we also, for the new construction, is already adopted 2021. But we have SECO, which is State Energy Conservation Office, has a program for local governments, and we are, as Noresco, we're one of the contracted vendors to provide energy audits for the local government buildings. So even though there are not like associated penalties, but at least we are encouraging these buildings to increase their performances and efficiencies. So just kind of high level, who is Noresco? We are a leading energy engineering firm, and we provide services for both new construction and existing buildings nationwide. Based in Austin, we have offices nationwide. We are a carrier company, and we have various subgroups, and I'm part of the sustainability group. And today I'll be representing the sustainability group, and our expertise is in energy audits, retro commissioning, TAB, and energy modeling. So what is an energy audit? So according to PNNL, energy audit is an assessment to determine where, when, why, and how an energy is used in a facility, and to identify opportunities to improve efficiency. So ASHRAE, there are like different levels, and obviously the easiest one is the Energy Star benchmarking, but ASHRAE categorizes them into three, level 1, 2, and 3 audits. And each level adds complexity and detail on the previous level, obviously. And also the time takes to put together these reports are also different. So for like level 1, it's more like a month. For level 2, it is more like 2 months. And for level 3, it's like 4 months. And ASHRAE Standard 211 regulates the energy audits, the tasks, and the reporting requirements. So as I mentioned, like each level is adding additional need to the other one. So for example, in general, for like level 1, or for all audits, like they review historical data, review construction drawings or available BAS information, space functions and things like that. So this is kind of like required for all levels. But for example, BAS trend review is required for level 2 and 3 audits. Or for example, in terms of calculations, simple calculations are okay for level 1, but bin calculations, which I will be getting into the upcoming slides, are required for level 2, and energy models are required for level 3 audits. Or like the life cycle cost analysis, for example, are required for level 3 audits. And it's similar for the reporting, again, like facility descriptions, historical energy use, benchmarking, low cost, no cost measures, or the ECMs, and the general like overviews of these measures are required for all levels, but more cost related calculations or LCCA risk assessments are required for level 3 audits. So I'll be getting into a couple of examples to show the differences between these audits. So goal of an energy audit is to identify areas of improvement and to reduce energy, cost, and carbon emissions. So it requires a whole building approach, which differentiates it from the retro commissioning scope, where we are like, it basically paints the full picture of the building, from envelope to mechanical systems, from O&M procedures to renewable energy sources. And so in general, to understand the building as a whole. And most of the time, our findings are also addressing some of the code compliance problems, or in general, just simply improving the occupant comfort besides the efficiency gains. In Noresco, our audit process starts with a kickoff meeting to establish goals, and discuss facility information, from building operations to, again, MEP systems, past retrofits to planned projects, or existing issues that the building is currently dealing with, just to understand what's going on in the building. And based on again, I mentioned on the previous slide, based on the audit type, the collected information changes, or the details changes. So that is also an important piece to know what type of audit we're going to be doing. And for the other one is for the ownership of the building, is leased versus owned. That kind of changes our prioritization for the ECMs if it is a short-term lease building. So the high capital ECMs will probably not be recommended, and things like that. And the next is basically getting into the site investigations and the site visits. So typically we ask at least 12 months of utility data, and hopefully 36 months, and construction drawings, and any other like nameplate information, anything that is available. However, we rarely obtain all this information in advance. And it could be based on the age of the building, or the property management maybe changed a lot, so they do not have this information anymore. And the BAS, sometimes if we can get the remote access, it's perfect, but sometimes we have to get the screenshots or any information we can on the site. And also the retrofit history is very important for us to understand, especially if things have changed since the construction. But probably most important, like most probably the design information is not applicable anymore for most of these projects due to the retrofits or the damages. I will be showing in some of the examples in upcoming slides. So the next step will be our detailed site visit. So during the walkthrough, we try to collect as much information as possible by taking pictures, taking measurements of temperature, humidity, flow, based on the need, or the CO2 levels, and interviewing the on-site personnel, which is really critical because they are the ones who have the best knowledge about the building and its operations and its problems. And lastly, if there's any BAS data is available, and we try to capture that when we are on site, especially if there's no remote access. And we pretty much have a pretty good idea about the measures at this point. And we categorize them into two. Low-cost, no-cost measures are typically the RCMs that have a very short payback periods, and the other one is the ECMs, the capital measures. This is what I was talking about. So some of this information is like so many retrofits have happened in some of these buildings, and so we try to gather this nameplate information, especially to be able to capture the age and the capacity. And so the model number and serial number are really critical for us. But even when you collect that, still deciphering these information is really hard, and we have to use some online references to be able to figure out these information, because then eventually these information will affect the operation of the unit. And as I mentioned, in terms of the information collection, the site visit is important, but also to be able to capture the existing condition of the equipment is very critical. As you can see on this pictures for the units, so there's like severe hail damages, and this will most probably result in decrease in heat transfer capability, capacity, and efficiency of the equipment. And most likely we will be probably seeing these buildings, these equipment is running 24/7 and still not meeting the temperature or humidity requirements. So this kind of all will make sense, or like clogged pre-filter screens or closed dampers, things like that. So some of this information will not be, sometimes the trend data will help us to understand like there's certain things are not, like the operation is not right, but when we see this equipment directly, we'll have a better understanding of what's going on. Also, like as you can see in this table, like some of the units are still using R22 refrigerants, which are phased out, and so we can at least address some of the other the O&M also related to information after our site visits. But even though we are mostly focusing on the HVAC system, which is the biggest consumer of the building, typically heating, cooling, fans, pumps, heat rejection and all, but there are also other inputs. This is, as I mentioned initially, this is like a whole building approach. So we still need to understand the other factors like lighting, lighting controls, interior, exterior lights, exit lights, plug loads, if there are any kitchen loads in it, any refrigeration loads, process loads, any IT rooms. Or for construction, there's like windows, walls, roof, have they replaced? Is it, low E glazing right now? Or what is the infiltration in the building? Or just in general, like what are the thermostat controls? So we try to understand as much as we can, so then we can address the problem areas. And the next is the analysis and the reporting phase, where we spend most of our time. We start with the utility rate analysis, and then kind of get into more energy cost and consumption benchmarking, degree day analysis, distribution analysis, and it cost distribution analysis, and the actual calculations of the ECMs and RCMs. So we first analyze utility data, which I mentioned earlier. We require at least 2 to 3 years to account for the seasonal variations and patterns of energy use. And we identify anomalies by just looking into this degree day graph. As you can see, like not just in the winter months, but also in the shoulder seasons, the gas usage. And this is a fire station from one of the projects I worked on. So the usage is very high. So this kind of like, even before going to the site, we kind of like, this kind of gives us an idea where we need to be focusing on. And the next is also looking into that. So even though like maybe the gas usage is showing anomaly, but the energy use distribution kind of tells us if this is something we should be prioritizing. Because if the gas, especially in Texas climate, if the gas usage is like 5% of the overall breakdown, so maybe it's not worth to spend our time on. But in this case, this was taking 36% of the energy. So this was something that we prioritized during our measure identification. And the second is, again, these are all high level stuff before. Sometimes we do it before even going to the site. Sometimes we do it after the site visit, but this typically helps to make sense of our findings. And the other part is the EUI calculation, obviously the national average based on the building type. This data is from Energy Star. So it is giving us the worst case scenario where the energy usage should be at the highest level. And even when we are looking into the for 1 year data for these sites, and some of these here are fire stations or police departments, we saw they're way higher than the national average. So this definitely tells us that there's something going on and we need to help them to fix. And the last is the energy breakdown, similar to the energy use distribution. So now we're getting into like the subcategories of where these energy users and which one we should be focusing on. So we, as I mentioned, we categorize RCM versus ECM, but sometimes this could be interchanging based on the utility structure or existing operation and some other factors. Sometimes an LED replacement actually could be a RCM based on the simple payback period. So as a rule of thumb, though, we consider any measure that is that simple payback period is less than 1 year is a low cost measure. And typically these are the control related measures. So this is an interesting picture that I took on site, which is I think really funny. I mean, improving thermostat controls are like the #1 ECM we recommend all the time, and especially, and it doesn't matter what type of building, this is always an issue because you're intermingling with people's comfort levels. And so apparently this building had a problem before. They mentioned, please don't turn the AC all the way down. And it was once they did this, the roof iced up and stopped working, and the thermostat was set all the way down. So that's why they recommended leaving it at 72. But if you see in the picture, it was actually set to 65, but the unit was able to make 70. And I was with my my measurement device, and it was showing 71. So there are multiple things wrong in this in this picture. But so in general, we typically do this measurements just to see if the sensor calibrations are good, which this was within 2 degrees, so it was okay. But again, like the occupants were not really complying with what the building owners or maintenance personnel is trying to achieve. So so typically they if they can implement this, if they can make sure that occupants are not overriding the set points, then in a couple less than a year or in less than 2 years, they should be able to show the savings. And the others are like, obviously depends on the HVAC type. More complicated systems, then we get into more like temperature, pressure optimizations or operator optimizations. So operator sometimes is tricky because sometimes we see the operator dampers are close in the buildings, and that is actually not bringing the minimum operator that's required as a code violation. But on the other hand, now opening the damper will cause more energy. And so it's actually will be turning into a penalty, but we still want to correct the operation, obviously. But if everything is working fine, then we implement the demand control ventilation for the areas that are applicable by code to save energy. And the other one is another typical one is the optimum start and stop. We typically see units are running. So there could be different problems like the ones I showed, if there's like severe damages on the unit, if the unit cannot make its set point, so it's running longer, or sometimes the facilities directly set them to come 5 hours or 4 hours earlier than the occupancy to make sure that the temperature is met. So when this type of scenarios are happen, then we recommend them a more optimized, more dynamic control on the runtime. And the last is, this is now getting into more retrocommissioning, but correcting the ongoing operational issue like stuck dampers, simultaneous heating and cooling, or the faulty sensors. And for ECMs, obviously could be a lot of things. I just put the ones that we mostly recommend. And I also showed a couple of examples from our recent projects for an LED retrofit or for an HVAC replacement. For LED retrofit, obviously it's no brainer anymore. Like everybody should already have retrofitted with LED. It's that they are really very cheap, and the simple payback will be pretty short comparing to other measures. And lighting controls with the occupancy sensors, motion sensors, the lighting sensors. There are different technologies available. And for HVAC replacement or the water heater replacements, we typically use the ASHRAE equipment life expectancy chart. That helps us if the equipment is actually end of its life. So is it actually a good time to replace it? And with that typically matches with also the operational problems that we are seeing. So if there's no damage, but if the equipment is already ended its life, so we typically recommend that replacement. Sometimes if it is a split unit, we just recommend an auto rear unit replacement, or if they have already done some load reduction measures, like if they already changed their windows or the lighting, so now the load in the building has changed. So sometimes we recommend a downsizing of the units as well. And obviously the solar panels are really popular these days, so we recommend them, or the envelope improvements typically takes way longer periods, but for lighting, we typically estimate is like 3 to 10 years, HVAC 7 to 25 years, renewable 15 to 25 years, or like for BAS 4 to 12 years. So these are typically our go-to ECMs. So when it comes to the calculations, so there are different ways. Pretty much audit level determines which calculation methodology we will use. For level 1 and 1.5 audits, we try to use the spreadsheet calculations, which are very quick, based on fundamentals like heat transfer basics, and requires lots of assumptions. Like if we don't know the U value or the R value of the envelope, there are some tables that are pre-developed that we can use. Or for example, if you don't have a trend data, so if we have trend data, we can figure out the heating season hours and cooling season hours. But if that's not available, there's some tables we can use for, and this spreadsheets are built for Texas specifically. So we can look at Houston or Austin, so we can find the most appropriate hours for that. And they give us a pretty, so especially our interpretation of levels, like for level 1, we said our accuracy needs to be within 30%. And so these calculations are giving us that accuracy. And for level 2, obviously now the accuracy becomes more stringent. Now we're saying we need to be within 10 to 20%. And so there are different ways. So ASHRAE requires detailed calculations, could be bin. For level 3, it's obviously energy model, but for level 2, at Noresco, we have 2 ways. It's either the bin calculations or the energy model. And typically these are determined by these factors, the time budgets of the project, which are the most critical ones, and the complexity of the systems, accuracy that we're trying to achieve, and the skill set of the engineer. So we try to pick either strategy, but typically they are within 20%. So before going to that, anyone who is not familiar with the bin calculations, so each bin, which is generated by a software called a bin generator, each bin contains the number of average hours of occurrence of a particular range of temperature, or like a weather condition. It could be like in our case, there's a dry bulb temperature and a wet bulb temperature. So this is this is generated through a TMY file or an AMY file. some type of a weather file, then we can generate this hours. So this kind of gives us a more accurate representation of the heating or cooling hours. And and for the energy model, as you see, we use Design Builder as our interface and Energy Plus as our simulation engine. So I wanted to show like a quick comparison. So while bin is like quicker and less complicated, still more complicated than the other initial spreadsheet that I showed, but still it sacrifices the accuracy, and there's also no feedback loop between the systems, especially when it comes to, like, for example, this quick example is for a chill water reset. For the bin analysis, like now we know that the temperature ranges, the bin hours, but we need to assume so we kind of followed ASHRAE's guideline. We're going to have between 60 and 80 degree outside air. We're going to have 10 degree delta T in the chill water. So changing it from 45 to 55. But we don't exactly know it should be 47 on this bin. So we kind of have to do less of assumptions. And in the end, it is showing us 38,000 kilowatt hour. But obviously with bin or without bin, when you use outside air for the basically the changing parameter, there's no feedback from the building. Maybe, and especially we know we are already sacrificing the ambient hours when we are raising the chill water temperature. So we want to see what is the maximum. I guess we all know ASHRAE requires 300 for the maximum ambient hours that a building should have. So there's no feedback loop. And now I wanted to show a couple of other examples from the model, because now with the model, we can do more complicated stuff. And one example is, again, it's just a comparison bin versus the model for the same outside air reset. We're showing pretty similar results, but again, there's no feedback loop. The model is showing is actually increasing 107 hours. And the next one is based on the supplier temperature. Now when we're using the sensor as the discharger temperature of the air handling unit, comparing it against the set point, and then kind of flagging accordingly, and then kind of modulating the chill water temperature. Based on that, we are seeing it's showing similar on hours. But so the important thing is we know, like based on our flagging condition, for example, we're seeing if it is not making the temperature more than 2 degrees, flag it. We could reduce it down to 1 degree, or we can say if one coil is requesting more, for example, flow, then start reducing the temperature. At least we know it is in our control. And the last one is, I think, the most interesting one is the valve position. So this is basically looking into every chill water valve, and then this calculate if the valve is more than 90% open, then we are starting flagging. And if there's more than this many valves are open, let's start reducing the temperature or increasing the temperature. But this actually showed, like while the outside air reset was showing 3% savings, this actually showed 7.2% while also having less unmet hours. So this is kind of where I guess we can say the energy model becomes more important if you want to get into this level of analysis for a project. So while we're talking about the energy model, and this is obviously a no-brainer for the IBPSA community, but I just want to kind of define it again, or the highlights why energy model is more accurate, but also more complicated than a spreadsheet, as in this definition. We're basically creating a digital replica of an existing building, and which is also based on a computer-based analytical model. Physics-based analytical model. So yeah, obviously there is pros and cons. Like now energy model requires more inputs, more time to do the analysis, or also the capability to run those codes. And maybe the project's budget is actually not applicable for that. So it is all pros and cons. Maybe if you're okay within 2-3% accuracy difference, so obviously going with the bin option is more realistic. But if you want to do a really deep dive, really accurate calculations, then energy model is preferred. And one important factor of energy model calculations is the interactive effects, because with the spreadsheet calculation, there's no feedback loop. Also, every measure is calculated independently, so interactive effects are ignored, unfortunately, when there's some manually. So this example is showing when this was an industrial facility which has a very high electricity usage in a year, that even these these each individual ECMs are modeled, but when you just sum them versus when you group them, the delta is actually 700,000 kilowatt hour, which was kind of corresponding to 3% of the annual electricity of that building. So this could be misleading in terms of savings or again, in general, the resets could be fighting with each other. So there's no way you can capture that when you run them individually and sum them individually. And the next one is, now this is more on the RCX side, but it's more like kind of looking into the faulty operation. This is, especially if you have BAS data, this is what we typically spend our time on. I want to highlight the O&M. O&M is probably the most critical factor after the measures are designed and constructed, and O&M becomes the most important piece to be able to make sure that these actual controls are running correctly. Because if the sensor goes out of calibration, you can see in that example. So in this example, there are 5 outside air handling units, and they all have their individual outside air sensors, which is great. They can, like, now they're like, you increase the redundancy if one of them goes bad, so at least the other one is working fine. But at some point, you also need to make sure that they're not within, like, they're not more than 2 degrees apart from each other. So because I know when I was in the building, they were all kind of placed at the same level at the similar areas. So there's no way they can have like this much of a difference in terms of the outside air reading. And this is not even comparing to the AMY data. So this is just a comparison between each other. The other part is, like, we see this a lot with the VFDs. So when you add a VFD, you assume that it's going to modulate, you're going to save energy, but we mostly see they're actually locked to a certain speed. They're not really utilizing the capabilities of the VFD. So we can see this operation, and we can mimic this in an energy model. Or minimum flow speeds, like if we're a chill water pump or a hot water pump, we see this, the minimum speeds are actually fixed at like 50%. So you're not actually giving much space to save energy on the pump. But as I mentioned, so there is like ways to capture this operation, this incorrect operation in an energy model, especially with Energy Plus. You can also mimic the faulty sensors. Like, these are some examples for like outside air, dry bulb, wet bulb, like chill water, outlet temperature. So you can actually create the actual digital replica of that faulty operation. So that's kind of like a segue to the O&M. That's why we always include O&M recommendations for each building based on the buildings, obviously. So this one is just only focusing on the air side, but if the building also has a central plan, so we always include our O&M recommendations in our report, because that is what is going to make these controls actually work. Like you can see, so like the previous example I showed about chill water reset was relying on either discharge air temperature or discharge air sensor to be working correctly, or the valves are operating correctly. So if you don't actually make sure these sensors or the valves are not getting the like semi-annual or 1 to 2 year maintenance, then there's no way this controls will work correctly. And the last portion for our, steps is the report, which for every level, every audit level, we include the executive summary, facility descriptions, utility bill analysis, recommended measures, future recommendations in case like the existing infrastructure is not available. So we also include that for the future considerations. And then O&M procedures, funding options, which is very critical, especially if the project is in a disadvantaged area, or like they have limited resources. So these funding options, and especially I know in Texas for local governments, they're really good funding options. So they could utilize them for their projects. And conclusions and the next steps. So sometimes based on the contract, we also help with the construction and MMB, measurement and verification of the projects, the implementations. Sometimes our work stops at the report and hoping that they will implement them correctly. But this is typically what for every audit level includes. So from that one, I will just be showing a couple like case studies or my findings that I think is worth to share with you. So one of them is AMY versus TMY3 comparison. So we know AMY, actual meteorological year data, is obviously because you specify a location, it's not from the airport, it is more accurate, it is capturing the terrain and everything around the site more accurately. So this, for example, this project was in Houston, and we had to use Bush Airport that was kind of closest to the site, but still you are using a data that probably is from 19 something to 2005. Whereas like we know with the climate change, like things are changing. So this is a very like basic comparison. And we were trying to like figure out like what was our gas calibration problems. Like as you can see from May to August, it's good, but also you're not using the gas, like it's only for the water heater or maybe the kitchen, but you want to capture the January, December to February, like you want to capture the shape correctly. So, and you see with the TMY and AMY, they're complete different profiles. And then when we actually compare the outsider drywall temperature, because also the system was running off of the outsider control, the boilers were locking based on outsider temperature. And so, yeah, we can see that clearly when we look at this, that's winter months, the temperature is very different between these two data sets. So it helps with the accuracy, it helps with time saving, so you don't have to play with different parameters for the calibration, and it also helps with the forecasting. Yeah, so when we are decided on the route to go instead of the bin, the calibration route, or the energy model route, that means the first thing we need to do is utility calibration. And these two examples are like, I just wanted to show different sizes. One was 800,000 square feet industrial building, the other one was a 9,000 square feet courthouse, and we still had to comply with, so when you, especially with level 3, you have to comply with ASHRAE guideline 14 in terms of the accuracy. For mean bias error, it needs to be within 5%, and severe MSE needs to be within 15%. So one of the examples, so these are like I mentioned about like our typical ECMs, but sometimes we actually get deeper into like, because we saw so many other problems. So the first thing is, this is a very old 93-year-old. So this is the same building, the courthouse building, 9,000 square feet. It is a very old building, but they have already done LED retrofit, and they replaced their windows to low E. And within the time, they had so many retrofits, but 13 years ago, they also retrofitted their HVAC system to heat pumps. But when I was in the building, they were having problems with meeting the set points. And obviously, like when even those heat pump systems are single zone systems, so not like every room gets the air, especially if you have not done the tab or the balancing work correctly. So some rooms were hot, some rooms were cold, the air was not distributed properly. So there were so many problems. And on the other hand, they did not have any outdoor air intake or exhaust. So this is a code violation, and they did not have hot water, and that's another code violation. So we, and also because it was an old building, the ceiling height was very low and they needed extra space. So that basically told us that we need to, our ECM should be on the VRF. And so they can have simultaneous heating and cooling load. And we can also have like better comfort in every zone will have its own indoor unit, and we can gain space. We don't have to have the duct work, maybe just for the DOS unit, because we have to couple it with a DOS unit to overcome the outside air problem. But they, instead of having 8 heat pump units, now they will only have 1 outside air units. And so we looked at the code for like the minimum ventilation rates, and we basically come up with a design, like a preliminary design for them, which also includes all the controls. And we kind of show them the implementation cost, like ballpark, what it's going to be, and what is a simple payback. So because the VRF system is a very efficient system, we were actually showing almost 50% savings, energy savings, even though the implementation cost is really high. It was showing 29-year payback. And we also did recommend like in case this is too expensive, they cannot go for it. If they replace the current heat pump units that are showing problems, it was actually showing very similar payback periods. So we are trying to show various options based on the budget of the client, but this was an interesting study that I wanted to share. And sometimes our findings are not really energy related. So this is a fire station, and they had a attic space which has a fire sprinkler wet sprinkler system. Even though they are kind of compliant with the code because they put the insulation between conditioned and unconditioned space, but they put it on the kind of ceiling of the first floor or the floor of the attic space. But because the heads are still on the close to the roof deck, and there is no insulation on the roof deck, and initially the complaint was the sprinkler system gets freeze every year, and they paint the ceiling, they changed it to drywall and paint the ceiling every year. So then we kind of like did a quick calculation, and we saw the space temperature actually gets below 40 degrees for 386 hours per year. And because the floor, I guess insulation was not helping the head. So our recommendation, and also this is another code violation because the plumbing or fire code requires that space, if you have a wet system, have to maintain 40-degree temperature, space temperature. So we recommended either going with the R38 insulation, which is a current code requirement for that climate zone. I think even R21 should be fine. But they will need to put some type of space heater to just to make sure that that space never goes below 40 degrees. So this ECM itself, like putting the R38 insulation, will not gonna pay back in maybe in 30 years because the impact it's gonna have on the heating and cooling load will be not significant. And so just having that insulation for the whole roof will be very expensive. But in order to comply with the code and not having this maintenance problems, they should have this solution. And for this one, it's like sometimes our ECMs could be very quick because we start with looking into the utility rates, and sometimes we see like this one on the right, the meter was either broken or having some issues on the gas, so they did not have any consumption mentioned for the winter season, but they were still charged. And so we helped the client to ask the utility provider to come and check their utility meter, what is wrong with that. Or we saw there's another client who was actually on a residential rate, and while they were a very small commercial building, and we did a market search for them, and we did not really negotiate it on behalf of them, but we just basically looked at a couple options, and we showed them like they were on 19 cents per kilowatt hour, which is a very high rate in Texas, and they were actually able to save $100,000 if they move with this other provider that we recommended. And as I mentioned, solar is very popular, so mostly we were asked to include a solar feasibility no matter what. And this buildings, again, in Texas. But so the client had this extra land, which has the trees, and they were really interested into utilizing this land to turning this into a solar farm. So we did our preliminary analysis, kind of putting the panels everywhere that we can, even including that yard, but still it was not offsetting the electricity 100%, but also they were already on a really good rate, so like 4 cents per kilowatt hour. So it's gonna it takes 57 years for them to pay back, which is not realistic. And also cutting the trees in order to put a solar farm was not really good idea in terms of carbon offset. So we basically said this project is not feasible. And this one is actually, this project showed a feasible, like for either one, like we're just showing preliminary feasibility. Obviously they need to do the, if they are going to move forward with the ground, they need to do geotechnical assessments, or if it's going to be on the roof, they need to do the structural assessments or more detailed electrical assessments to make sure that this project is actually feasible. But our analysis are just more focusing on the energy side. So for this example, this again in Texas, this project was interested in, they're a transit company, and they were interested in converting their current fleet to electric. And so we basically did a quick calculation based on number of like buses they currently have, what is the battery, like how big the battery is going to be, and how much additional demand it's going to be on the meter. And so we actually calculated like this and it was a very small office building, but but the consumption like that will be required for EV will be 388,000. So it's way higher than their current consumption of the building. So we looked at multiple options, and again, their utility rates were kind of high on the high end. Their solar radiation was really good. The orientation was good. So there are multiple factors obviously affect this, and it's like I guess our conclusion was this project was very feasible, but again, they still need to do this additional analysis on the structural or the geotechnical side to make sure that this project is actually good to go. And also the extra land they had is very desertic, so it's not like requiring to cutting any trees or anything. So the cost associated to that is also going to be obviously cheaper. For this one, I think this is the last one I have. So sometimes it's not like, sometimes when we go to the site, we realize that, or even during the kickoff call, that the client is actually in the process of, converting their current building to something else. So for this one, the building was originally built for an office, but they were thinking to converting more than 50% of it to a warehouse. So that will obviously for us immediately gave us like ideas how we can save energy, because the number of, even though the number of people, I think these numbers were not that different, but the plug loads will be much lower, or the thermostat set points. Now we don't have to really meet 73 anymore. And we didn't even get into like the run hours and a couple other stuff by just like converting the actual need or the load of this new spaces. We immediately come up with an idea, so it's instead of just kind of coming up with a complete new design, they could actually, so they currently had 95 rooftop units, and they were all operational. They were like 10-year-old or so they're in a good shape. And we just said, instead of coming up with a complete new design, you could just easily eliminate some of the units. And then our calculations showed they could eliminate 42 of the 5-ton units. It's obviously average, so they need to still do like shifting, making sure that each space get enough air and stuff. But our just sizing comparisons show like they could actually reduce their cooling capacity from 572 to 359, and same for the heating, same for the airflow. So this could even be a cheaper project for them instead of the new design, just elimination of the existing units. And I think their electricity savings were showing around 400,000 kilowatt hour and $30,000 in terms of cost. So yeah, if the existing units are in good shape, and I mean, this is obviously not a case for every building, but for this project, it was an interesting study, so I wanted to share. So with that, thank you for listening. I can take any question you have, and I know I need to also show the slide. And that's all I have.
Thank you, Elvin. It looks like we have a question in the chat for you. Not sure if you can see that, or you would like me to read it for you.
Let me see. Yes. What will be your guidance for level 1 and level 2 audits? Sorry, any cost per square meter range will help provide quick estimates. Yes, that's a question that we're asked constantly from our clients. Unfortunately, I don't have that data with me. But so guidance is like, obviously, like a more like a deeper dive will be more like will help to save more energy, because we'll be looking into more options and help them in even implementation and so, but it will be cost heavy. But level 1 is it's just a walkthrough, like you don't really get much out of level 1. So I would say we typically do level 2 audits, and for our federal projects, or for which are more like EPC side, or for like the government related projects or state related projects, we typically do level 3 audits. So I would say you will probably get the most out of from level 2 and 3 audits. But unfortunately, I don't have the cost information available. Let me see. I think this is the only one that I can see. Let me know if you see anything else.
Nope, that should do it. So we will wrap up for today. Thank you, Elvin, and thank you for everyone joining today. As you can see on your screen, please check out SimBuild 2024 website for the latest updates, and we'll encourage you to submit program ideas, presentations, and session proposals. Deadline for those is January 12th. For those of you watching us on YouTube, please like the video and subscribe to our YouTube channel. If you'd like to follow up with us, please feel free to reach out at admin@IBPSA-US. And I just want to thank everyone, and I hope you all have a wonderful rest of your day.
Thank you. Thank you for having me.
Thank you.
Bye.